Hello, everybody. My name is Pierre Cristofari, and I'm currently at Duluth at the Observatories of Paris. And thank you very much for reaching out to the very high energy gamma ray domain. And what I want to do today in my short intervention is to talk about very high energy gamma ray domain. And it's a very brief introduction to the field. So if you do know anything about the gamma ray domain, you might want to fall asleep for 10 minutes. And if you don't, this might be interesting for you. And so it's a very simple introduction. So don't mind any questions. This is a picture of the Cherenkov Telescope Array, CTA, currently being built on two sites in Chile and in La Palma. And you see here that you have different telescopes and different size. You have what we call the small size telescope, the medium size telescope, and the large size telescope. So different names for the different sizes. And just to give you a sense of what it's like, this is a close-up picture on the large size telescope. So this is a 23 meters telescope already built. Here, this is in La Palma. And the first light was around December 2018, I think. And for obvious reasons, the prototype has been built on site directly. So this is already installed, and the rest of it is going to come in a few years. So this is one example of a gamma ray observatoire, which is CTA. And you have, of course, different observatoires already working, different places in the world. This is a LASSO instrument in China, and the Large High Altitude Air Shower Observatory. Already working and providing data and publishing data. This is another instrument that you might have heard of, which is the HESS telescope, the High Energy Stereoscopic System in Namibia. And this is an array a bit smaller than the previous one that I showed. This is only 5 telescopes, but it's also taking data and providing good science. The principle of all this instrument is pretty much the same all the time. You have a source of gamma rays somewhere producing gamma rays, and gamma rays coming to the atmosphere produce a shower of particles, and these particles, a shower of particles, produce a Cherenkov light that you can detect with an array of telescope. And that's what, for example, what is done. This is a principle of any of those, but for example, S that I just mentioned. And this will be the case for Veritas, Magic, and CTA. All these different instruments, they work pretty much with the same principle. On the two sides that you'll have for CTA, just to give you also a sense of how many telescopes we have, on the south side, you have 14 middle-sized telescope and 33 small-sized telescope, though the small size is already a 4-meter thing. And on the north side, 4 large-sized telescope and 9 middle-sized telescope. So lots of telescopes. And this is here a couple of plots with the prediction for what it's going to look like and what's going to be once it's built. So on the left, you have the flux sensitivity as a function of energy, so the sensitivity plot. And on the right, you have the angular resolution. So for the energy sensitivity here, so you don't really care about all those plots, but this is previous instrument, currently observing instrument, and you have next generation. And of course, you're going lower in sensitivity with the next instruments. But what you want to look at is the energy, the typical energies. This is a 10 TV, this is 100 TV. So you see that the various instruments will be improved from the TV range to the multi-TV range, 100 TV. So this is where we are working and what we're interested in. So TV being 10 TV, meaning 10 to the 13 electron volt, right? And on the right, you have the typical angular resolution as a function of energy again. So this is for CTA. If you look at the thick lines, the black and the red dashed line here, and you see that this is a few arc minutes. So in the previous talk by Professor Barre, I heard arc second. So this is something, I don't know what it is. So we're talking about a few arc minutes, and this is where we are in the TV world. The main scientific project, and this is, for example, what is to be found in the paper of CTA, Science with CTA in 2017. So they're divided in 3 themes. The first one being the origin and the role of relativistic particles. So basically understanding where cosmic rays come from, how they are accelerated, and how they propagate in the galaxy. The second theme is to be able to probe extreme environment, understanding merger of black holes, neutron star, black hole merger, but also anything connected with jets, relativistic jets and winds and explosion, everything extreme. And the third theme in the CTA paper and the main scientific project is let's say, other themes like nature and distribution of dark matter, understanding how it is distributed, and also more exotic themes like Lorentz invariance violation. And in order to address those different topics, we are going to be looking at different sources, and we're already looking at different sources. So classifying them from galactic to extragalactic. This would be, for instance, the galactic center and the supermassive black hole, the galactic plane survey, the star forming regions, the Magellanic Cloud, starburst galaxies, but also transients, AGN, jets, clusters of galaxies, many different objects producing very high energy gamma rays. So I'm not going to be talking about all of them, but what I propose to do is just to mention a few cases, a few scientific cases that I think biasly are very interesting. Why do we care about Athena? Well, for us, looking from the gamma ray domain, Athena is providing, or the X-ray domain is providing two things, the thermal emission, making us able to understand high velocity outflows, shock, and also different properties of the environment and of the plasma, the temperatures, and also the energetics involved, and also the non-thermal X-ray emission, which enable us to probe the acceleration of particles at very high energy, especially electrons, and also to understand the maximum energy reached by particles, understanding the magnetic field strength and structure potentially, and the different ratio from electron to proton, which is, so this is a very simplistic view of Athena from what it looks like when we look from the very high energy domain. So the three things I want to mention are, the first of all is AGNs, then to talk about supernova remnants very briefly, and then the search for pevatrons. So AGNs, for an obvious region, is really that it's a fine example of all the things we want to do in the gamma ray domain. We want to be able to understand AGNs, to do a spectral energy distribution across the entire electromagnetic spectrum. This is a famous example of Mark-IN 421. And so you see here from the radio to the very high energy domain has been monitored. We want to be able to understand the variability in time. So this is also another famous example. This is PKS 2155 minus 304. And you see on time scales, which are minutes here, the variability. So this is the integrated flux above 50 GeV, I think, yes, 50 GeV. And you see that we've been monitoring different flares for these objects and also for a variety of other AGNs. And finally, recently, for another object, which is Centaurus A, a radio galaxy, we've been able to detect the extended emission from an object for the first time, not from an object, from an AGN for the first time. So you see here, this is a typical PSF here. This is the green thing, and the white contour here correspond to the extended emission from Centaurus A. So we want to be able to look at the spectral energy distribution across the entire spectrum, the variability in time, and also now we're capable of looking at the extension. So it's very important for us to understand these things and put them together with the rest of the electromagnetic spectrum. A second scientific case is understanding the gamma rays from supernova remnants. And I know there's going to be a talk. There's going to be a talk right after about the extended jets from AGN, I think, by Dr. Poquet. And this is going to be talked about by Dr. Gustav, I think, this afternoon. So gamma rays from supernova remnants in the very high energy domain. There's an ever-ending question, which is, where do gamma rays come from? Do they come from protons interacting with the interstellar medium, or do they come from electrons interacting with soft photons? And if you look at the literature, it's very hard to understand. People have been debating over this for many years. And here, this is the famous example of RxJ 1713, a supernova remnants very well studied in the very high energy domain and also in the X-ray domain. And we've been now able to provide, when I say we, I mean the community. So we've been able to understand the profile, the extension of this emission in the X-ray domain and in the gamma ray domain. And so the next generation is expected to do this even better by an order of magnitude. And to finally answer the question, what is the gamma ray emission coming from? Is it hadronic? Is it leptonic? Is it due to the protons or the electrons? Also here, adding on this slide, an example of the spectral energy distribution across the entire magnetic spectrum from the radio domain to the very high energy domain here. And you see that for this object, the previous generation of hard X-ray instrument, Suzaku, has been provided very important intel on what is the spectrum here in the X-ray domain. And the third example that I wanted to mention here in this short presentation is the hunt for Pevatron. Is very biased because it's something I'm very interested in. And the story goes like this. If you look at the spectrum of cosmic rays here, this is the local spectrum, so what we measured at the Earth in the very famous plot, we see that you have a remarkable power law in energy up to somewhere, which is called the Ni, at about 3 PV 10 to the 15 electron volt. And for a long time, people have been wondering what is producing this remarkable feature, the remarkable slope and this spectrum in general. And if we focus only on the energy up to the Ni, we know that for a couple of reasons, supernova remnants should be capable of producing this. The first reason being that there's a mechanism, the shock wave, that is the supernova remnants, can accelerate particles with a power law in energy, which is compatible with what we observe here. And we know also that since you have a remarkable power law in energy up to somewhere where it breaks, we expect the sources to be pevatrons. We expect that they can accelerate particles up to 10 to the 15 electron volt. And in other words, we are looking for pevatrons in the very high energy domain as to look for the sources of galactic cosmic rays, for the sources of all these particles here up to the Ni, up to the Ni. And recently, one of the instruments that I showed in introduction, a LASSO instrument, I discovered that there are about at least 12 pevatrons in the galaxy, but not completely answering the question because all these sources, so LASSO instrument doesn't have a very good resolution. I mentioned a few arc minutes for CTA, but for LASSO it's not as good. So the 12 sources, not very well understood yet, but we've been able to understand that they apparently are not supernova remnants. So it opens the question, what are those pevatrons? Are supernova remnants pevatrons? Can we understand which are the accelerator of cosmic rays up to the PV range? At the same time, other instruments, HESS, that I mentioned also, the thing in Namibia, has been detected what we think are a couple of pevatrons. On the left, you have the spectrum and the image associated to the galactic center, Sagittarius A star. And on the right, you have a new object, which is called J1702 here, also with an extended spectrum that looked like a pevatron, and also we don't know yet what it is. But still, the search for pevatrons is very preoccupying and very important for the gamma ray community because we think it's also solving the mystery that is the origin of cosmic rays. And we believe that study across the multi-wavelength might help identifying what are the pevatrons, also test for different modeling. For example, here on the bottom panel on the left here, you have a synthetic spectrum of what a pevatron is supposed to look like, if it's a supernova remnant pevatron. And you see that in the X-ray domain, we might be able to understand, using the X-ray domain, which is over here, the green line, we might be able to constrain the different models and to understand if a source is or is not a pevatron. So that's about it. Yeah, and those X-rays coming from secondary electrons. So as a slide of conclusion, the final conclusion, what I wanted to say is that CTA, SWGO, LASSO, SOC, all these names are for instruments in the very high energy gamma ray domain. They will observe the sky together and also with Athena. Say soon enough, but you know the timescale has been discussed. With the next generation of instrument, we'll have, of course, unprecedented performance, and we'll be able to provide an entire survey of the galactic, of the sky, in the TV and in the multi-TV range with systematic survey. We have a variety of scientific themes, transient neutrinos, pevatrons, supernova remnants, on and on. And I think that the study with the X-ray domain is not only nice, but needed to understand most of these topics here that I mentioned here. But thank you very much for your attention.
So thank you very much, Pierre. So in your talk, I see a lot of conversion from cosmic ray to gamma rays to X-rays. How much do we know this conversion to get reliable quantification?
Sorry, by conversion, you mean?
How to convert, for example, gamma ray to X-rays. And so you have a lot of physical quantity in that. How much do we know to get a good mapping of cosmic rays or gamma rays?
If I understand correctly, the question is how much, how precise are the modeling
Exactly.
using the very,
what would be missing to get reliable modeling?
I think, I mean, two things that are missing now and we'll be getting in the coming years are the improved sensitivity, resolution in energy, and the improved resolution in the angular resolution that we're currently missing in the gamma ray domain. This is, from what I understand, because I've always used X-ray results as already published, but this is not something you're lacking. I mean, the energy resolution and the sensitivity is something that to go back to the X-ray domain is something that you're already very good at. So that's why we're eager to make the connection between the very high energy domain and the X-ray domain. But for now, what we're lacking is I think the performance to resolve many sources and to understand clearly what's the energy resolution, the energy distribution.
Okay, thank you very much. So hello, everybody. First, I would like to thank the organizer for inviting me to talk about the X-ray observation of radio-quiet AGN and the supermassive black hole winds outflow. So here on the second slide, just let's start with the well-known unified scheme of AGN. This is of course simplistic, but just to show the different components of AGN. You have here the supermassive black hole at the center, you have the accretion disk, you have the physics of the accretion disk that Didier already mentioned you in his talk, you have the broad line region, the narrow line region further out, and you have the molecular dusty stories around, and depending on the line of sight, you have Cepheid 1, Cepheid 2, and you have also what we call the wind outflows. And I will talk about this component also in this talk. And you have some jets and external lobes, but this has already discussed in the Pierre Cristofari talk, and I will focus on this talk on radio-quiet AGN, so without any jets or external lobes. So the first part of this talk is dedicated to absorption feature in radio-quiet AGN. X-ray spectra, it means the warm absorber, Didier has already talked about that, ultra-fast outflows, and also the interstellar medium along the line of sight. So first, I would like to talk about the warm absorber and the ultra-fast outflows. This is post-ionized gas located at the AGN rest frame that are viewed along our line of sight. And you have here an example of bright AGN MR2255. It's not the same than Pierre just talked about. It was PKS 2255, but here is a radio-quiet AGN, and you can see that in this the residual in sigma that there is a lot of absorption line from carbon to sulfur, and including also what we could say the iron M shell UTA feature here. This warm absorber is detected in about 50 or up to 65% of nearby AGN. So it's a very common feature observed in AGN. In general, this is multi-phase medium. This means that you have different components with different column density, different ionization parameters. And you have also that this is this outflowing media with a relatively moderate outflowing velocity. And when you calculate the kinematic luminosity, it's about 1% of the luminosity, the bolometric luminosity. So you can say this is slow, but if you had all this amount of matter processed over the AGN lifetimes, let's say a few hundred million years, million years, sorry, it could be really significant. And then there is also some feature that observe at higher energy. They are highly blue shifted iron line of around 25 and around 26, while the rest frame energy of are about 7 keV, and you can see that is very highly blue shifted. And then they showed you that this outflowing feature are very high outflow velocity up to 0.3 C, and could be even higher when you take into account the special relativity effects. And these UFOs are also common feature observed in nearby in AGN, not only nearby AGN, but in AGN. And compared to warm absorber, there are higher column density, higher ionization parameters, and also the kinematic luminosity is much higher compared to the warm absorber components. And therefore, UFOs have been proposed to be a prime candidate for feedback and to explain also the supermassive black hole galaxy host relation. So here it's just an artist view of what we call the winds from the accretion disk. So it had been proposed that the UFOs are the inner part of the wind outflow, so located very near to the supermassive black hole in the inner part of the accretion disk, and the warm absorber could be the part much further out from the accretion disk and further out the supermassive black hole. And you can see that here in blue is in fact where the winds here. So you can see that it's a hollow conical bipolar stratified winds. And what is also important is that this is not only observed in nearby AGN, these UFOs, but also observed in high redshift AGN. For example, in a very recent study from Chartas 2021, in a sample of 14 IZ AGN with about 1.4 to 3.9, it's mean near the peak of AGN and star formation activity. This is detected in almost all the AGN. So you can see that UFOs are present at different redshift and over a long time scale of the universe, and could be indeed a very good candidate for AGN feedback. So here it's let's say a picture showing you the different feedback at different spatial scale from micro. I put here the distance, and the micro, meso, and micro are much larger. So here the UFO are located in this very small region very close to the black hole, and then you can have also the warm absorber and interaction of this outflow with, for example, the molecular outflows. And what is really interesting is that there is more and more evidences that there is some AGN where UFOs are detected in X-rays and also possess some molecular outflows detected with ALMA, IRAM, and NOEMA, for example. And here you have, from Lara and collaborators, a graph showing you the molecular mass outflows versus the luminosity of the AGN. And you can see a very nice correlation between these two characteristics. So it seems the UFOs have very high impact on the AGN evolution and also for the feedback process. If you want to know much more about AGN winds, I would recommend you to have a look on this address, this internet address, where they have a different presentation that was presented during a conference on disco winds at last September. So here it's Athena XIFU simulation of UFOs prepared by Didier Barret and collaborators. Here it's an example of AGN called PDS 456. It's at really moderate redshift, but very high luminosity. And you can see that you have, with XIFU, with the sensitivity and the spectral resolution, we'll have the possibility to follow with high signal over noise ratio the change of the UFO properties, and also, for example, to disentangle the different components at different velocities. And for example, here you have 100 kiloseconds, it corresponds to 10 ERG for a black hole mass of PDS 456. So you can see that you can really probe the UFOs in a very small spatial scale. So it's very important. And also with the sensitivity of Athena, we will, in XIFU, will be able to determine the output properties for quasar with redshift up to 4. So here is an example of this quasar with a redshift of 2.6. Here you have this because this is the observed energy frames. That's why it's redshifted, because of the redshift of the AGN. And you can see the UFOs of this AGN that is simulated with XIFU, and you will see that we will have a very high signals over noise to really study this UFO in nearby AGN up to higher Z QSO. So in the meantime, there will be also GRISM and the Resolve calorimeter on board. That will be a very fruitful pathfinder for Athena XIFU science for such topics, but also other topics using point sources. So, of course, there are in the spectra of AGN, you can see the warm absorber, the UFOs, but you can also see galactic interstellar medium seen along a line of sight of bright AGN. Here, it's an example taken with the ARGS on board XMM. And it's the case of Arcan 120. It's a bright bare AGN. A bare AGN is when you have the hollow conical winds, but you don't intercept with the line of sight. You don't intercept the warm absorber or the UFOs on the line of sight. And then you have a very clean continuum in the soft part to detect the galactic interstellar features. And you can see in this spectra a very significant absorption feature from the neutral oxygen from the galactic interstellar medium. And I would like to point out that there is several models already exist in XPECT to adjust interstellar medium feature and also dust that will be developed also very recently. It's continued to be developed in the preparation of GRISM and Athena. So there is a lot of opportunity for the member of the PCMI who are interested to look at X-ray bright sources to study the different phase of the interstellar medium. So here it's a simulation with XIFU for a bright AGN. It's marking on 4:1. And here is a simulation of only 10 kiloseconds, so it's very short on X-rays for the nitrogen KH at different ionization stage, from neutral to very high ionized stage. And you can see that we will have, again, a high signal over noise to study this photo absorption from nitrogen, but you have also from carbon, oxygen, and so on. For the interstellar medium, you have also complementary study that can be done along the line of sight of bright X-ray sources, like the bright low mass X-ray binaries. And I would like to refer to the Elisa Costantini talk, also along the line of sight of the gamma ray burst to study the interstellar medium in the host galaxy of the gamma ray burst and the intergalactic medium. And I would like to refer to Tayyaba Zafar talks just after this talk. And also the multi-wavelengths, which is very important, the multi-wavelengths, let's say, study of interstellar medium that Antoine Gusdorf will talk about later this afternoon. So I've talked about the absorption feature, but now I would like to talk about the emission feature we see in radioquake AGN. From the disk corona system, the broad-line region, the narrow-line region, and the molecular torus. Of course, compared to this very simplistic view of AGN, in the last, let's say, years, we find that the different components are clumpy, and there is also presence of dust inside, for example, the broad-line and narrow-line region and of the torus. You can see that there is a lot of clumpiness and dust around AGN. And here it's a schematic view of the different radius where you can have no dust. Here you have only large grain around above the sublimation sphere. So you have dusty borderline region, and then you can have the full dust, we say the full dust. So at each scale, spatial scale, you can have clumpiness and dust inside the AGN. And I would like to refer to Guang Yong talk about the spectral energy distribution fit of AGN using SIGALIX that implements clumpy torus and also polar dust extension. So now I would like to show you an example of what we can do with X-ray fine spectroscopy to learn more about the physics of the broadline region. And it's based on X-ray plasma diagnostics. Here again, I will show you the example of Argon 120 per AGN with no warm absorber. So you can see the emission line from the matter out of the line of sight, and only in emission. So it gives you a very clean view of the emission line. And also it's collected from galactic absorption I showed you just before from the oxygen one. So here there is only the soft X-ray emission line from helium-like ions, from nitrogen to magnesium, and also from hydrogen-like ions from nitrogen to magnesium again. And from the line profile of this line, this is in fact the helium-like ions are in fact triplets line. I will show you after that, I will explain much more about that. But when we fit the three lines with the same velocity, we find that the velocity profile of the helium-like triplets is similar to the one we observe for the optical lines from the broadline region. So it seems that this helium-like triplet comes from the broadline region, and the velocity profile of the hydrogen-like ions come from the narrow line. And from the plasma diagnostic that we'll explain much after that is based on the helium-like triplets. And from these helium-like triplets, we can infer the density of this of the medium emitting this soft X-ray emission line, and we find that the density is about 10 to 11 centimeters per square, and it's really similar to what we know about the broadline region. Also, you have here the ionization parameters that is linked to the luminosity of the AGN, the density of the emitting region, and the localization of the emitting region. When you know the ionization parameter in the fit, from the fit, you have also, also the luminosity of the AGN. We have from the plasma diagnostic infer the density. You can infer the localization of the emission region, and we found that is again really similar to the broadline region localization. Such broadline from helium-like have been also reported for several other AGN, and it seems that broadline origin for the soft X-ray emission may be common in AGN. So it's show you really the powerful tools that can be done with plasma diagnostics. So here I would like to focus more about the X-ray plasma diagnostic that we can do with helium-like emission line. This is triplet, but in fact this is a quadruplet. But the quadruplet can only be, in fact, you have the resonance line, the anticombination line, and the forbidden line. And the anticombination line is formed by two lines. But these two lines can only really be separated above the calcium and so on for very high Z ions, very high Z atom, in fact. So these diagnostics were first widely used for the sun and was developed by Gabriel and Jordan in 1969. And you can deduce the density comparing the forbidden line and the anticombination line, and the temperatures for the for collisional plasma when you compare forbidden the sum of the forbidden and anticombination line compared to the resonance line. And also these diagnostics, since of course 1969 for the sun, have been extended to other type of astrophysical plasma to be used for the spectroscopy allowed by XMM and Chandra. And these diagnostics allow us to infer the physical process. So it's very interesting because you can really disentangle the different physical process. For example, you can determine your plasma is photon ionized, like in AGN X-ray binaries. If this is collisional plasma, like you can have in stellar corona or cluster of galaxy. You can also study out of equilibrium plasma in time with the ionizing and the recombination phase. You will have different feature of this ratio of line. It will be developed by Rolf Meve in the 80s and also by Yuan Liedal in 1999. And maybe what is more relevant for the PCMI is that you can also probe charge exchange. A charge exchange is when you have a highly charged ion that collides a neutral atom or molecules. And this has been developed in Denel to 2010 in L'Allemand, and you can really have, let's say, to determine the physical process with charge exchange. So the interest of the X-ray plasma diagnostics is that you can, with the different helium-like ions, you can probe different range of density. Here it's the range of density, here and the temperature, and you can see that the low charge ion, for example, the carbon here, you can probe density around 10 to the 9, and then when you increase with the ion, you can probe more and more density. They are sensitive to much higher density, and then for each ion, you can really probe different density domains, and you can, when you had all this, probe so density and temperature domain over several decades for all type of AGN, for all type of object from stellar corona to AGN. And thanks to GRISM with resolved in Athena and ZIFU, we'll be able to extend the use of the X-ray plasma diagnostics at higher density and higher temperatures for sulfur and iron, because you will be like that. So it shows the really powerful tool we can done with the next generation calorimeters aboard GRISM in Athena. And if you want to learn more about helium-like triplet diagnostic, I will refer to a review that I done with Jacques Dubois and Nicolas Grosso when we gathered together a lot of information about what we can do with this plasma diagnostics. So as a summary, I would like to say that X-ray can probe the close environment of AGN, from the disk corona to the molecular dusty torus, and we can infer with the X-ray the physical properties of the different media. For example, the ionization parameter, the density, the column density, the geometry, and the composition is very important. Also, as I showed before, AGN winds are very promising candidate to explain supermassive black hole galaxy Earth feedback. And there are more and more evidences of IGN showing both UFOs and molecular outflows. And there seems to have a very tight link between them. X-ray fine spectroscopy of the interstellar medium from the cold to hot phase along the line of sight of X-ray bright sources are already possible with XMM RGS and Chandra LOTG to see the galactic interstellar medium, but also the intergalactic medium. And the X-ray plasma diagnostics using emission line from the helium-like ions can be a very powerful tool to discriminate the ionization process, electron, photon, and charge transfer, and also to study the out of equilibrium plasma. Also, we can infer very important physical properties like density, temperature. You have also with the higher charge ion with what we call the satellite line, very close to the helium-like triplet, you can infer if you have a thermal or non-thermal electron distribution, the ionic fraction, and so on. So I would like to say that we can already done a lot of very nice science with XMM and Chandra, and there will be very soon say, a huge step forward for X-ray fine spectroscopy with GRISM, and of course with Athena in the next decades. And I will finish there. I think that I was maybe rather fast, but I did not want to show you too many things on AGN. I want really to focus on the things that really may be more relevant for PCMI. So thank you for your attention.
Thank you very much. You're right on time, actually.
Okay, so perfect. Thank
so
you.
I have a question from Quentin Salome.
Mm-hmm.
Will Athena have the combination of spatial and spectral resolution to be able to image the ultra-fast outflow? We will be able to observe how far they extend.
Oh, let's say that the UFOs are really in the inner part of the AGN. So we will, with Athena, what will be very important is that with the sensibility, you will have a kind of, we will be able to follow the variability of the outflows, but you cannot, let's say, spatially resolve it. But what you can do already with Chandra, for example, and a very nice spatial resolution in nearby AGN, you can really have a look on the winds outflows, when you can see the some shock features on the ISM medium and so on. But what is important for Athena and also for GRISM is that you will be able to follow the variability of the UFOs, and then also to really track the different spatial, let's say, component of the stratified winds. I hope that I answered the questions. But if not, we can discuss on that later on.
Yeah, I have another question from Ellen So. Do you see or expect to see with Athena signature for shock formation in the various flows which can be probed?
I think so, because, for example, there are some shock. If you have a very, for example, for charge exchange, you can find that if you have a very ionized ion that collides neutral or molecular medium, you can find such a feature from the helium-like triplets. Will be very different, for example, for electronic collision excitation. So yes, indeed, we will be able to have such a feature that we can see with X-ray plasma diagnostics. And for the spatial resolution, it depends on the final spatial resolution of, as shown by Didier just before. But in nearby AGN, for example, NGC 4051 or 5151, I think that there's things that we can see the different components.
Okay, thank you. I have another question from Jérôme Petit about oxygen 7. Does radiative transfer play any role, or are the line only optically thin?
Oh, there is a lot of things that we can do also with the, here I told you about the, let's say, optical thin, but you can have a resonance scattering inside, and you can reprobe resonance scattering with these helium-like triplets. So depending on the line of sight of what you observed, you can have impact on your helium-like triplet line. So yes, we can do such a thing. And what was the, sorry, the beginning of the question? I think
the line optically thin.
Yes, so this we can, this is optically thin, but we can also probe some resonance scattering.
Okay.
Due to optically thick.
So I think I have a last question from Ludovic Bienier. Concerning charge exchange and laboratory data needs, could you tell if the cross-section for the processes are well known for a variety of colliding partners and collision energies?
Okay, so I will just, if I remember, yeah, it's just an example of what was done, for example, between the charge exchange between Iron-26 and nitrogen-2 for the charge exchange. And this is for direct electronic impact excitation. You can see that the relative emission of the different line, the forbidden line, atomic emission line, and the resonance line are very different. And there is already some experiments that are done for different, let's say, molecules or different kind of molecules, for example, N2, but you can have also H2 and so on. And it could differ between the different, let's say, collided atoms or molecules. So, but for the different kind, I was not able to find if we have all the information for the different molecules that exist for in molecular outflows and so on, because I don't have access to such a publication. Oh. So this is maybe something we can have for discussion maybe during the roundtables about what we need to prepare Athena. I think.
Yeah, sure. We should discuss that. Okay, so thank you, Delphine. So we now can go to the next talk. So the next talk is from Tayaba Zafa, who will tell us about gamma ray observation. So Tayaba, can you share your screen?
Sorry, I just have to stop sharing. Sorry. So you are there. Thank you.
Thank you.
Thank you. Thank you very much. Okay, I will start sharing my screen. Yeah, I hope you are able to see it.
We do see it.
Yes, thank you. Thank you. First of all, I thank you and thank all the organizers for reaching me out and asking me to present the case for Athena. I will cover mostly about gamma ray burst and their interstellar media studies. More work on dust, for which the X-ray is very important, and later on I will go and talk about Athena and its contribution it can provide to gamma ray bursts. So GRBs, as we know, are excellent probes to study interstellar media, as they are, of course, extragalactic, and they can, when they shine, they can tell us about their environments, like the gas, metals, and dust living in there. And that is very important if you want to know understand the galaxy at high redshift, which is typically very faint, but only a gamma ray burst triggering, shining it out and give us all the information of these faint structures in the universe. Now, these gamma ray bursts are of two types, as we know. First, I will talk here about the long duration gamma ray bursts. These are the gamma ray bursts which have the gamma ray burst gamma trigger of more than 2 seconds. And these gamma ray bursts, which I will come to the short one later, which are actually more popular these days because of their association with the gravitational waves. But going back to long duration gamma ray bursts, these are, as we know, of course, both short or long, but they are very bright. For these long ones, it is typically very important to see them very bright, as these, if they are distant, they are coming from very faint galaxies. And as I said already about the redshift range, so they can occur in the nearby universe, can occur to the very famous one also at redshift 8. There are claims of redshift 9 or 10 gamma ray bursts also, but the one at redshift 8 is the one which is spectroscopically confirmed. Long duration gamma ray bursts occur usually in very dense medium, so they have very high hydrogen column densities, typically more than 10 to the 22 square centimeter per square centimeter. And as it goes for these long duration gamma ray bursts, they have very simple spectral shape. Normally simple single or double power law can easily fit them. I will show you some examples. But to see the feature that which power law they are after, if it's a single or a double or a broken power law, as we call, we need X-ray. And that is very important, as optical or infrared cannot tell us everything. And as it goes for the long duration gamma ray bursts, these are occurring mostly in star forming regions. These are galaxies which are producing stars, and these stars at the end are bursting out as hypernova, what we call more powerful than supernova, and we see them as a gamma ray trigger, and we call them gamma rays. Now, as these are transient sources, so of course they have problems, so we need to chase them rapidly. whenever they appear on the sky. So they have the problem that they appear on the sky and they could last from few minutes to few days. So they fade very rapidly. And that's why we need these target of opportunity observations, the TEO, to track these. And then GRBs as being very intense and very powerful. If there is some dust around them, they can also, that dust can GRB radiation can influence the dust and it can crack, which is important for my kind of studies. I will show you a little bit later. So how we observe these gamma ray bursts? Normally, we are after their spectral energy distribution. As I said, that only optical or infrared cannot tell us much. Barre was earlier talking about the multi-messenger astronomy, and for GRB, it is very true. We have a Stargate, what we call a consortium, which is tracking these GRBs at every possible wavelength which we can go for. So if we just take the optical or infrared observation and we want to see that how we can fit their spectral energy distribution, because they are supposed to be either a single or broken power law, then only that optical or infrared regime cannot tell us much usually, or the information we estimate from those might be, for example, wrong. As there could be a break between the optical and infrared somewhere here, between the two, between the X-ray and optical infrared, and we might miss it out and misinterpret the slope. And then as it goes for studies like this, where there is a dust, we misinterpret that either. So we need X-ray data. Currently, it is coming from the SWIFT satellite, which is doing most of the GRB observations and giving us the X-ray spectra, although Integral and Fermi and other are contributing, but SWIFT is a dedicated satellite for GRBs. So SWIFT energy range is also very important, typically matching to what Athena has. This is going from the soft X-ray to the hard X-ray, and can give us the hardness ratio or other properties from the X-ray if we are after those. I will come to the absorption later, although, as I said, that we can misinterpret, for example, dust, as the light loss in the optical usually is due to dust. So we can misinterpret is if we are not incorporating X-ray, but what about this absorption in X-ray? I will come back to that later, but normally, just to let you know, apart from this soft X-ray absorption, we can pretty much fit the spectrum of the GRB very well. And we can infer if it could be a single or broken power law very easily, while X-ray optical has more problem, as dust based on the redshift could be moved away or closer to us if it is nearby GRB. So as now we are in this era of X-shooter, where our Stargate consortium is trying to acquire every possible GRB which is observable with the X-shooter, which is a spectrograph which runs from the ultraviolet to the infrared and give us the whole spectrum coverage from the optical to the infrared, or I can say the far UV to the infrared in one shot. So X-ray, after we get the trigger from the SWIFT satellite, have the gamma ray and the X-ray spectrum, we chase them with X-shooter, as we want to build that spectral energy distribution as longer as possible. And X-shooter is also very interesting in a sense that if we happen to see something kind of like a Milky Way type of dust, which I will also touch that later a little bit, then we can cover it. Again, if we don't have X-ray, we can misinterpret the spectral slope and we can get whatever this Milky Way type dust will look like. I will show you some examples later. We can misinterpret it, that is it like, for example, Milky Way or LMC or something else. We can misinterpret that. So X-ray is very important to interpret the spectral shape very well. Now here are some examples where actually there is no dust, what we see like a Milky Way type, but there is something like small Magellanic type where we do not see any feature. So in this case, we can see that X-ray was very important. For example, this one, whole of the optical to infrared was absorbed by dust, as the dust was up to 1 magnitude or more in that case. And if we just use the data in the X-ray and in the optical and infrared, we might not be able to get a good shape of the extinction curve. But once we included the X-ray data, although after all the absorption, we can get a better handle of the slope, but it looks like, and can fit the extinction curve very well, SED and hence the extinction curve, I would say. And this is the kind of test which we were running, that do everything looks the same? Are we going to imagine that everything looks like Milky Way, LMC or SMC? And in this case, we run a sample where we tested that using the X-shooter data and X-ray data, that can we see something different or similar to the Magellanic Clouds or Milky Way. So we find that there are cases which actually look to have same kind of extinctions as in the Small Magellanic Cloud, but there are other cases also existing which give us actually extinction different than the Small Magellanic type cloud. Why first we started with Small Magellanic Cloud is because mostly for gamma ray burst, as it goes for mostly high redshift thing, is that the Milky Way type dust is very rare, and we see things in dust which are mostly featureless. Now going a step further, just to tell you that these are the extinction curves which look like. I showed you the bump, which was actually inverse. So when you observe it in absorption, of course, it looks like absorption. And here we just reverse it. And that's why now the bump, the same one which you've seen before in X-shooter spectra, now it looks like emission, but actually it's just the reverse or flipped version of it. So blue one is the Milky Way and the green one is the Large Magellanic Cloud. And they both have an absorption feature in the middle at optical wavelengths. And that bump is, of course, changing its shape, moving from one sight line to the other, while SMC is the one which has no feature. And that's what you have seen. While our studies after inclusion of X-ray data suggest that, yes, it is this kind of featureless extinction curve present, but they are not necessarily similar to be what we see in the Small Magellanic type extinction curves. So here is an example where we try to catch all the featureless extinction curves, which are like Small Magellanic type extinction curve, and try to see how they vary. Even if we see the Small Magellanic Cloud, it has these dashed lines extinction curves, which are all different. So whatever we see as average, even for that side, that particular Magellanic Cloud is not true. So there is a variation, extinction curves moving from one value to another, where this RV parameter, which we use to estimate extinction, is very important. The smaller it is, the more steep your curve will go. And we find that here is this Small Magellanic type extinction curve, which has an RV of, for example, 2.9, if number really matter. The difference is just 0.3 as we go, but you can see how steeper extinction curves go. And that is what we see for gamma ray bursts. Even steeper extinction curves we found for quasar, and Jorge before was talking about AGN or other people, although it wasn't about dust. But even for those, if we talk about dust, this thing is keep varying, and it is very important to get the best spectral energy distribution if possible, and that's why X-ray data inclusion is very important, and then infer the dust properties very well, as they can then tell you that what kind of environment these GRBs are living in. Now, including this, using this information, we went on seeing that how dust is then varying at higher redshift. If we wouldn't have X-ray, we wouldn't be able to do this study. So these are all the cases where we have spectra plus X-ray, and the SEDs all the way from infrared to the X-ray. We build them, and we find that as we go on to higher redshift, we just put an arbitrary cutoff at the redshift 3.5. We see lesser and lesser dust because there are many GRBs which are present in this region, of course, not as populated as before, but we see more and more little dust as we go on to higher redshifts. So that was actually then a problem for us. That is it the dust real or is it observational bias? And we find there aren't any observational bias. All these different colors are telling that we tested for different observational biases, where the blue and the gray are the regions which X-shooter cannot observe if you have a very faint or dusty GRB at those redshift, while this is the range which it can still populate, but even for half a magnitude of dusty GRB, we never have seen that. So we might be missing and they don't exist. And if they don't exist, it means less dust at higher redshifts. So that's why it was very important to have these full SEDs as longer as possible. Now going back, as I showed earlier, that we could have obtained Milky Way type of extinction curve. And that was very important. All these colors you see here, so far there are 5 gamma ray bursts which are seen with having a Milky Way type of extinction curve. And we see a bump there. Again, as it goes for SMC, we find there is a variation. They could be very flat, they could be very steep, and meaning that parameter which we try to measure them, they are all they are varying from very small, for example, in this case to 2.1, to very large, in this case 4.5. If the number really matters, I would say that this is for us, for dust studies, it is very important because it is telling the smaller the number, the more smaller the grains there will be, and the larger the number, the more larger grains there will be. Or in this case, if we have this kind of extinction curve, we will get carbon at the end. Or if we have, for example, SMC type extinction curve, then we have more silicates in that environment. So that's why it is very important if we want to understand all these sorts of things. Now, as earlier I said that there is absorption there, and it won't be affecting us much because there is still enough X-ray data that we can observe the spectral energy distribution very well. But this absorption is also not unimportant. It is very important to understand, because this X-ray absorption is actually measuring all elements, whether they are in ionized or even in solid phase present in there. So it is providing us the total census of the metal column density, what we call in these gamma ray bursts. Although we write it as NHX, but it is not only hydrogen column density, but as I said, it is a representative of the total metal column densities of these GRBs. And this total metal column is usually very higher. I will show you an example later, but from what we infer from only gas column density, this one is usually very higher. So when we compare this hydrogen absorption, what we call column density obtained from hydrogen absorption with, for example, dust, we find that, of course, if we have the local group, for example, Milky Way and our Magellanic Cloud somewhere here, they follow the same trend for this total metal column density. But once we plug in GRBs, they always have higher column densities obtained from X-ray for every GRB, I would say. So there is nothing which looks similar to the local group. But what we find interestingly from these gamma ray bursts is that if we put a cut of higher redshift bursts, we find that all the redshift, for example, greater than 3, have more higher column densities compared to the ones which are at lower redshift. Now, this could be as a result of the growing intergalactic medium. As we go on to higher redshift or larger distances, the more and more hydrogen along your way you can expect, and that intergalactic medium might be giving you a higher metal column or hydrogen, equivalent hydrogen column density. Now, to understand this, that is it just true if we provide one single cut, or what if we go on and provide various cuts? So we go from redshift 1 to redshift 1 and 2, or for example, from 2 to 4. Of course, as I showed you before, that as we go on higher redshift, our numbers go down as we don't have much observation there, but still, for all the cases where we can estimate both X-ray absorbed column density and the extinction, we put those in, and we find, if you can see, this slope is always varying as we go on from one to the other redshift panel. And this is actually telling us that, yes, of course, there might be more intergalactic absorption in there. But as Watson interpreted in his work was that there could be helium in these ionized H2 regions, or metals ejected by those stars could be dominant X-ray absorption sources in those cases. So helium could be responsible in these ionized regions, as it was found in that study. And when we compare this hydrogen X-ray absorption hydrogen column density to the gas phase hydrogen column density, because GRBs also give in the gas phase that how much Lyman alpha they have in absorbed form. So once we compare those, and again we provide the same cut where the black ones are high redshift, and you can see they are everywhere from here to here, and the blue ones are low redshift. Again, in this case, the redshift cut was supplied to be redshift 3. We find that actually we see things everywhere. So that's why X-ray was very important. And then we try to interpret that, can we get the same thing from the optical data? And we try to interpret it by correcting the hydrogen column density to the total metal column, which is observed either from iron or silicon or any metal. And we find that we can, if we provide this kind of mechanism where we correct our H1 column density, which I showed you before from absorption, from Lyman alpha, and correct it for metallicity, we can get the same thing. We can match up things very well. So that's why X-ray was very important. Without X-ray, we might be getting these things very differently. Now, going to short gamma ray burst, and as you know, this popular event of the gravitational wave 1708-17, where we got the LIGO chirp and 2 neutron stars mergers we find. That one was very important because it also gave us at that time the X-ray absorption, which we got very first. And that X-ray data, which was covered for several days, give us a lot of information. Although optical was very important to know the merger itself and the environment, but X-ray data contribution, mostly from Swift and Fermi and others, was very important. Now, as you know, both of these long or short duration GRBs, what this can GRB will look like in the era of Athena. So Athena won't go back because we have already in the intro, and Barrett was talking all about this wild field imager and XIFU, but energy range will be very important as it matches very much with the Swift. So we would not be very far off, but actually we are getting more than what Swift can give us. And there are already 2 science proposed for related to gamma ray bursts to cover these target of opportunity observation, which are signatures of first stars, where we need, of course, the target selection based on already, as the multi-messenger astronomy goes, already knowing the redshift and the brightness of the bursts from other media. And then there is also for warm, hot intergalactic medium filaments, where you want to understand the physical properties of that. Again, for gamma ray bursts, you need to know that if there is prompt brightness to chase these bursts or not. Covering both, first I will go to warm, hot intergalactic medium. It is very important as we want to know where are the missing baryons, and GRBs could be the sources if we want to track them, normally the low redshift ones. Already these WIM are found to be around 50%, where we don't know when we try to see the missing baryons in the universe. So they contribute around 30%, that where this contribution is coming from. And here almost 15% could be covered if we go on chasing the highly ionized oxygen. And Porke was already talking about highly ionized oxygen. And here is another example, which is coming from Castra, work from 2013. And there they use Athena again observation for the, simulations for the very low redshift gamma ray burst. And they try to see that can they map the WIMP very well, and how many lines they can cover. Of course, the sensitivity is higher, what you can do with Swift or other matching to Chandra. So more and more analysis could be done, and more details could be informed from about the WIM using gamma ray burst. And the next one is, of course, signatures of first stars. And that is very interesting if we want to cover, as I said, that we still have very low number of very high redshift GRBs, particularly above redshift 6. So if we want to increase that number, it is very important to chase them. And here is actually a simulated spectrum, what it will look like for a gamma ray burst with Athena if we are seeing it at redshift 7. And the spectrum will be brilliant compared to any other space observatories if you can go for. And of course, as it goes, that if you want to compare the gas column density or the total metal column density from X-ray, you can get it very well. So that's why it's very important getting more decent X-ray spectra and more decent SEDs at the end. And hence, even for individual observations, it is very important to have this X-ray coverage, and that Athena can only provide us in the future. Now, one thing which I find that there could be an interesting science case, which would be seeing the recent advancement in the gravitational wave astronomy and the short GRB contribution. That's why I given a little bit of information of short duration GRBs. So for short duration GRBs, although TO observations will be very important, as it will be, of course, a talk of the town those days if you see another gravitational wave event. But other thing is that these short duration GRBs, even if they don't go for prompt observation right after their trigger, late time observations of these short duration GRBs are also very important, because they can tell us about the GRB environments. For example, if there is any reionization of the ejecta at late times, then we can see after the merger happen, and we can see how much reionization in the environment can happen. Or for example, for these mergers where we want to estimate the magnetar spin luminosity, then X-ray data will be very important, especially covered from XIFU of Athena. That will allow us to estimate the X-ray emission will allow to estimate the magnetar spin luminosity very well, and get the whole magnetar model completely. So here are some examples where it has been tried with already observed gravitational wave 0817. So with all that, I would leave with my summary. I can see I'm a little up. So yes, I covered more both long and short duration GRBs and why they are very important, and why the X-ray is very important to cover their SEDs, and where Athena is already having some science cases listed for WIM, or for example for signatures of star, but more could be added, as Athena is covering the spectral range, which is very important for gamma ray bursts. So thank you.
Thank you very much, Tayaba. So it's very interesting how you show that the data attenuation curve is very central in all these observations. So I have one question from Jérôme Petit.
Yeah.
You use the extinction curve from LMC and apply them at very low visibility extinction. Could it be a problem? Are the extinction curve from LMC measured in the same domain of AV?
So, of course, that's why I was testing that. Should we think that everything is same and keep applying those? And in this case, I didn't apply. In my case, actually, I applied a free-form model to see that if they match at the end to LMC or not. So it was free-form. It's a parameterized model, which gives you at the end either it looks like SMC or not. So no prior resemblance being taken into the account.
So if you want to set up a good attenuation curve, what will be the most important? The extinction curves, the size distribution, or the chemical composition?
It should be the chemical composition. Really? That would be very important. Yeah.
The carbon to oxygen ratio.
Yeah.
Okay. So thank you very much.
Thank you.
So we are now reaching to the lunch time. So we're gonna make a lunch break and resume at 1:30 Paris time. Thank you very much to everybody.
Thank you.